Do you think implicit differentiation is the hardest part of Calculus 1? It's certainly up there. I know when I was taking calculus, that was definitely one of the hardest parts for me. So I want to show you an example of how we can do an implicit differentiation problem in the easiest possible way. It really just comes down to using one trick. So let's go ahead and just jump on into it, and I'll show you what I mean with an example. So here's the problem we're going to be going over today. We're going to find dy dx by implicit differentiation, and we are given the equation e to the x over y equals x minus y. So like I've been doing with a lot of my other implicit differentiation videos lately, we always want to start these out by first figuring out which of these letters is going to be our function and which of these letters is going to be our variable. Based on this thing right here, we're trying to find dy dx. That actually tells us right off the bat that y is going to be our function and x is going to be our variable. The reason why we know this is when you have this kind of notation, d of some letter over d of some letter, whatever's on top is always going to be your function, and whatever's on bottom is going to be your variable. So what that tells us is y is a function of x. X is the input variable, y is the output. And the reason why that's important is it tells us what we're going to be doing is taking the derivative of both sides of this equation with respect to x. So we're going to find d dx of this equation. If we had y on the bottom and x on the top, we would be instead finding d dy. But since we have x on the bottom, x is our variable, we're taking the derivative with respect to x. D dx is just the notation that means the derivative with respect to x. So the reason why this is important is if we take the derivative with respect to x of x itself, so in other words, you're taking the derivative of your variable, well, that derivative is just going to be 1. Pretty much what that means is any derivative that just has x's in it, it's going to behave the way that you expect it to. We can use power rule, chain rule, product rule, quotient rule as normal. However, if we're taking the derivative with respect to x of y, which is a function of x, an unknown function of x, since we don't know the function y, we don't know what it is in terms of x, we can't actually find its derivative, which is kind of weird, but what we can do instead is to say that the derivative of y with respect to x is just dy dx. So this notation here basically just means the derivative of our function y with respect to x, which is exactly what we're trying to find in this equation. So when we take the derivative with respect to x of this thing, this equation, what it's going to do is it's going to introduce a dy dx, which we can then solve for. So how do we do that? Well, we're pretty much just going to go through this equation and find the derivative of each of these terms separately, and then we'll be able to kind of put them all together. So first of all, the derivative of e to the x over y. This is actually, kind of a complex piece to find the derivative of. Because it has x's and y's in it, we're going to have to use the chain rule a couple of times here. So the chain rule says if we're taking the derivative of some function plugged into another function, you want to kind of figure out what's your inside function and what's your outside function. Well, typically when you have an exponential like this, or e raised up to some power, usually your power is going to be the inside function. So we're going to use chain rule here. We're going to treat e raised up to some power as our outside function, and the power itself as our inside function. So basically you could think of x over y as the inside, and e raised up to the x as our outside. So the e raised up to some power is kind of the important piece there. So by chain rule, in order to find the derivative of this whole thing, what we need to do is take the derivative of our outside function with our inside function left alone, still plugged into our outside function, or the derivative of our outside function. And then we need to multiply that by the derivative of the inside function. So basically, we need to take the derivative of our outside. Well, the derivative of e to the x is just e to the x. So taking the derivative of this outside function, leaving the inside function the same, is still just going to give us e to the x over y. And that's just because e to the x is the derivative of e to the x. And then what we have to do is multiply this by the derivative of our inside function. So then we have to multiply that by the derivative of x over y, which we'll get to in just a second. And then what we need to also do is take the derivative of the right side of our equation. So the derivative of the right side of our equation, we would just need to find the derivative of x. Well, we figured out already the derivative of x is just 1. And then we need to subtract the derivative of y, which again, we already figured that out, is just dy dx. Okay, so now we just have this other piece here to find the derivative of. We need to find the derivative of x over y. Well, that's a fraction. So that should tell you pretty clearly that we're going to have to use the quotient rule to do that. So the quotient rule is not too difficult to apply. It's pretty much just going to be a formula. I'll kind of make a little side problem of it over here. So when you're doing the quotient rule, you want to find the derivative with respect to x of some quotient x over y. Well, with the quotient rule, what that tells us is, let's say we're taking the derivative of some function, f over g, some unknown, numerator and denominator. To find the derivative of this, you would just do the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So we pretty much just need to figure out, we can kind of write out our f and our g, our f prime and g prime. So we'll just take f is the top function, so it's going to be x in this case. G is your bottom function, which is going to be y. Then we want to figure out the derivative of each of these, which again, the derivative of x is just 1, and the derivative of y is dy dx. And then we can just plug these four pieces into this formula. So we're going to get the bottom times the derivative of the top. So g, which is y, times 1, minus the top function f times the derivative of the bottom, so x times dy dx. And then that's going to be all over the bottom squared, so all over y squared. So this is the derivative of x over y. So now what we can do is kind of substitute this whole thing in right here. So now that we've taken the derivative of both sides of our equation, what we want to do next is expand everything out. So what I mean by that is we're pretty much just going to multiply this e to the x over y into the parentheses here. So that's going to give us e to the x over y times y, and then minus e to the x over y times x times dy dx. And that's all going to be over y squared. And then what we can do is split this fraction up. So we can basically write this as two separate fractions. So we would get y times e to the x over y squared minus x e to the x over y times dy dx over y squared. And then we can simplify this a bit. The y squared is going to cancel, one of the y's is going to cancel with this y. So we're just going to get e to the xy over y. There's nothing that can cancel with this, any of these y's down here in this one. And there's really no simplifying we can do over on the right side of our equation. So now what we want to do, now that we've kind of expanded everything out, is we want to get all of our dy dx terms on one side of the equation and all of our non-dy dx terms on the other side. We want to kind of get them separated. So this does not have a dy dx. We can go ahead and subtract that over to the other side. And then we do have a dy dx here, so we can add that over to this side. So now that everything on the left side of our equation has dy dx in common, what we can actually do is factor the dy dx out of the left side of our equation. So doing that is going to leave us with, if we pull a dy dx out from dy dx, that's just going to leave us with a 1 right there. You need to make sure to put that placeholder 1 there, because if you don't do that, kind of doing the opposite of distributing the dy dx into the parentheses won't give you this extra term out here. And then if we pull the dy dx out of this term, we're just going to be left with minus x e to the x over y squared equals 1 minus e to the x over y over y. And now that we have the whole left side of our equation just as dy dx times something else, we can move this whole other thing over to the other side by just dividing it over. So if we divide both sides by everything in the parentheses here, we'll just end up with dy dx equals everything over on the right side of our equation divided by everything in the parentheses here. And please do keep in mind, there is definitely some simplifying we can do from here. It's usually not a good idea to have fractions within fractions, but I'll leave that for you to finish up. From here, it really is just a matter of simplifying because we have solved for dy dx, and it is okay that we have that in terms of x and y. Since we didn't know what y was from the beginning, we can't really get it just in terms of x. So once you simplify that, that'll be your answer. See, that wasn't so bad, right? Well, I hope you found this video helpful. If you did, please be sure to hit that like button down below, hit that subscribe button and the bell icon as well. Those are great, free, easy ways to support the channel so I can keep making more videos like this. If you want to learn some more about implicit differentiation, just click on one of these videos over here. Thanks, and see you next time.